All right, in this section we're going to take what will seem like a bit of a diversion from the topics of the last sections and look at how we might approximate the area under a curve and then look at how we can actually find the exact area. Toward the end we're going to see what this all has to do with integration. So if we consider the following scenario, we have this function y equals x squared plus 1. Here's its graph, mostly in the first quadrant part of the graph. And let's suppose we want to find the area under this curve that's bounded by the x-axis and the lines x equals 0, x equals 4. So those are these lines here. Basically, we want to find the area of this region. Now, if this region were bounded by all straight lines, or maybe a combination of straight lines and perfectly circular arcs, we probably have some nice geometric formulas, but we're not really in that situation. It's just bounded by this curve, y equals x squared plus 1 at the top. So we can't quite, we don't have like these nice geometric formulas to find the exact area, so we're going to do the next best thing. And we're going to approximate it by just fitting some rectangles underneath. When we fit rectangles underneath the curve, we call them inscribed rectangles. If we use rectangles that fit over a curve, we call them circumscribed rectangles. We're going to focus mostly on the inscribed rectangles, although we will do some of the other ones as well. So here's that same function. Here's its graph. And we're going to use 4 inscribed rectangles. So I'm going to just draw the region again. I'm not going to do all the shading, but I'm just going to here's the region we're after. Now 4 inscribed rectangles. I'm going to make them all equal width. So the width of each rectangle, if they're all going to be equal width, is going to be the length of the whole interval divided by the number of rectangles. So the length of the whole interval from 0 to 4 is 4. We're using 4 rectangles. So the width of each rectangle in this case is going to be 1. This width of each rectangle, we call that our delta x. So I'm just going to mark out these distances of 1, or these widths of 1. Now they are inscribed rectangles, so here are the heights I'm using. And note that our function f of x that they gave us, or y, is increasing, right, as x goes from left to right. And so if I'm going to end up with inscribed rectangles, I have to use the left endpoint of each interval. Like if I look at the interval from 2 to 3, right, I have to use the 2, right, that left endpoint to define the height if I'm going to have a rectangle that fits underneath the curve. And so I'm just going to kind of jot that down. We get the height by using the left endpoint for inscribed rectangles. And we get the height, we use the left endpoint. Of course, the height itself is the y coordinate. So next, just going to find all of these points. So the first one is 0, 1. I'm just taking the x coordinate and then plugging it into x squared plus 1, that function. So at 1, 1 squared plus 1 is 2. At 2, 2 squared plus 1 is 5. And at 3, 3 squared plus 1 is 10. So those are all of our points. And we're going to use the y coordinates, those are our heights. So the approximate area using 4 rectangles, I'm going to denote that as a sub 4. This is the width times the length, right? Each rectangle is a width times a length. So I've got a width of 1 times, or I guess a width times a height, times a height of 1. There's the first rectangle. The next rectangle is a width of 1 times a height of 2. The third rectangle, this rectangle from 2 to 3, a width of 1 times a height of 5. And then last, a width of 1 times a height of 10. It might seem odd that I'm including the factor of 1. That's okay. I'm kind of just trying to illustrate how we put this together. If it seems odd that I'm including and writing the factor of 1, this next step is going to seem really weird. What I'm doing here is I am going to say, look, these all have a factor of, that common factor of, in this case, 1. I'm going to factor it out. We don't usually factor out a 1, but I'm doing it this time. So, and then what's left inside is 1 plus 2 plus 5 plus 10. And the reason I've done that is because this form is the one we're basically going to take, right? When we do other approximations. That form now is the width multiplied by the sum of the heights. Because we're using a uniform width. Now the sum of all the heights we indicate by taking a sum. We use this little sigma notation, and the heights are these f of x values. So this might be rewritten as delta x times the sum of our f of x values. And when you do this all out, when we have what, 15, 17, 18. Now here's one thing I can tell you for sure about the area under that curve, and that is that it is bigger than 18. I can tell that because I've used these inscribed rectangles. So look at all of these pieces. I haven't included these pieces I'm shading in. That's the parts I've left out, right? So I know that for sure that the area I want is going to be more than 18. So let's do this again. Same curve, same region, right, from 0 to 4. Only this time they say use 8 inscribed rectangles. Excuse me. Same region. This time we're using 8 inscribed rectangles, so our delta x is the interval length, so right minus left over number of rectangles. 4/8 is a half. So now I'm just sort of marking out the 1/2. Here are these rectangles. Still using inscribed rectangles. And now we need these points. But we already know some of them, right? Some of these are repeats from last time. So there's 0, 1, 1, 2, 2, 5, 3, 10. So we need these other ones. If you put in a half, 1/2 squared is a quarter plus 1 is 5/4. This is 3/2. If you square that and add 1, 9/4 plus 1 is 13/4. This is 5/2, and if you square that, 25/4 plus 1 is 29/4. And then here we have 7/2. Square that, 49/4 plus 1 is 53/4. Okay, so we have our y coordinates. Those are our heights. So when we find the area, the approximate area with 8 rectangles, I'm going to do the width times the sum of the heights. That width is 1/2, and then I'm going to add up all the heights. So those are all the y coordinates. 1 plus 5/4 plus 2 plus 13 quarters plus 5 plus 29 quarters plus 10 plus 53 quarters. Notice of all the heights, I should have, I'm using 8 inscribed rectangles. There should be 8 heights here, so you could just double check that you have them all. And there are 8 heights there. And if we add these up, we get 43. Cutting that in half gives us 21.5. Now there's 2 things I can tell you about the area under the curve. Like the last time, I could tell you for sure the area under the curve is more than 21.5 because again, these are inscribed rectangles. I can see, look at all this space, this area that I haven't included. But I can also tell you that this is a better approximation than the last one. I know that this approximate area with 8 rectangles and the approximate area with 4 rectangles are both underestimates. But this underestimate is bigger than the last one, which means I must be off by a lesser amount. This is closer. This is a better approximation. In general, the more rectangles that we use, the better our approximation will be. We could also use circumscribed rectangles. So I'm going to do one example with the circumscribed rectangles. Same region, right? So I know we've kind of been revisiting this region a bunch of times, but just to kind of get a sense for what we're doing here, we're going to use 4 circumscribed rectangles. So this is going to be an overestimate. So I've got the same region here. Our delta x is 1 because we're using 4 rectangles. But because I'm using circumscribed rectangles, I'm going to use the right endpoint. It's an increasing function, so I'm going to use the right endpoint to end up with circumscribed rectangles. This is a circumscribed rectangle, right? It's the stuff that's going to grab extra area. So the width, which is 1 times the sum of the heights. Now, notice I'm not using 0, 1 as one of the heights, right? Because I'm using the right endpoint. My first rectangle, I'm using the point 1, 2. Here's 2, 5, 3, 10. And then the last one is the one we didn't use before. This is 4, 17. So the sum of the heights is 2 plus 5 plus 10 plus 17, and this gives us 34. So what I know for sure is that the area is less than 34. That grabbed a bunch of extra area. So here I'm just going to kind of summarize what we've already seen. We're going to, when we approximate with n inscribed rectangles, we cut them up into always equal subintervals so that the width of each rectangle is just, you take the interval length, which is, if our interval is from A to B, you take the right minus the left to get that interval length and divide by n, the number of rectangles. When we pick the heights, we want to, on each subinterval, pick the x-coordinate that corresponds to the lower y-coordinate to get a rectangle that fits under the curve. If our function is always increasing, that means it's going to be the left endpoint. If it's always decreasing, it's going to be the right endpoint. And you should note that if your function is increasing and decreasing, you might have to switch endpoints. You might have to sometimes use the left endpoint and sometimes use the right endpoint. Always look at a graph. Of the function. Throw it into your calculator if you need to. And then we get the approximate area by taking the width and multiplying it by the sum of the heights. So here's one more. Here's a decreasing function, and we're going to use 6 inscribed rectangles to approximate the area under this curve from 1 to 4. So this region here. Our delta x is 4 minus 1 right endpoint minus left endpoint divided by 6, which is 3/6 or 1/2. Now if I'm going to use inscribed rectangles, this is a decreasing function, so I'm going to use the right endpoint. So this first point, for example, this is the x-coordinate is 1.5 or 3/2, and then the y-coordinate is 3 minus the square root of 3/2, right? And then so on for all the rest of these. Now I'm going to organize my work here rather than kind of try to fit everything in the diagram. I'm going to make a little table. My first coordinate that I'm going to use is 3/2, and then 2, and then 2.5 or 5/2, and then 3, and then 3.5 or 7/2, and then 4. There's 1, 2, 3, 4, 5, 6. Okay. Oops. So that first one is 3 minus the square root of 3/2. I'm just going to keep going. 3 minus the square root of 2. 3 minus the square root of 5/2. 3 minus the square root of 3. Now if I want to add all these up, I'll just note, let's see, so what we want to do is take delta x, multiply it by the sum of these heights. So it's 1/2 times. Now the sum of the heights, if I add all of these up, first of all I'm going to add 3 6 times, so that's 18 minus all the radicals. And that's how I'm going to write it out over here on the left. I've got 18 minus root 3 over 2 minus root 2 minus root 5/2 minus root 3 minus root 7/2 minus root 4, or I guess minus 2. And I'm going to do it all in one go. So 1/2 times 18 minus, I'm just going to plug all of this in. And I get 4.089 approximately. And there's approximate area using 6 rectangles. All right, so we know some general things, right? We know how to draw these, conceptually what we're doing, using when to use right endpoints or left endpoints. We know that the more rectangles we use, the better our approximation. If I want to get a really accurate approximation, maybe I want to use like 10 or 20 rectangles. But what if I want the exact area under a curve? That's what we're going to look at next. If I get a better approximation by using more and more rectangles, then it would stand to reason that to get the exact area, what I really need is to use infinitely many rectangles. So we're going to kind of build out this concept in this example. And I'm purposefully using a simple example for two reasons. One, the work will be, there's still a substantial amount of work to do, but it's really kind of doable with this simple-ish example. Kind of, it's enough to illustrate the concept of what we're doing. And also, it's going to be a region that we already know how to find the area of because it's a simple geometric region, and we're going to see that we get the same result. So it lends some validity to this process. So we're going to find the exact area under the graph of y equals 2x, above the x-axis and to the left of the line x equals 4. So, right, this region here. Now, we're first going to find the approximate area using n rectangles. I'm going to leave it at n. I'm not letting n be a particular number. What I'm going to end up with, we hope, is a formula with n, an expression with n that said if I wanted to use this many rectangles, I just have to plug in n to this formula. So our delta x, 4 minus 0 over n, or 4 over n. This first x coordinate, I'm going to call that x naught. And then, you know, these are ostensibly, these are really small values, right? So these are all of our rectangles. So here's x1, x2, and so on. We have lots more rectangles here, and then we have some at the end. This at the end, the very end of the interval at 4, that's x sub n. And so this one right before it is x sub n minus 1. This one here, x sub n minus 2. And we'll note that because this is an increasing function, we're using left endpoints. That means that we will use x naught to get one of our heights, but we will not use xn to get one of our heights. Right? The last x coordinate we'll use to get a height is x sub n minus 1. So I'm going to arrange this work like we did the last one. I'm going to make a little table. So our function f of x equals 2x. Now, our first x coordinate, x naught, we know, that's the one we know for sure what it is. It's 0, and of course its height is going to be 0 there, right? This is the flat line. x1, well, how do we get x1? We start at x naught and we add a width, right? One of our delta x values. So this is going to be 0 plus 4 over n, or 4 over n. And so its height is 2 times 4 over n, which I'm going to leave written in that form. x2, the next one, I'm going to add 4 over n again. We get each x sub I by just adding the width to the previous one. So x2 is 2 times 4 over n. And so this is using the function 2x. The height here is 2 times 4 over n, or 4 times 4 over n. And x3 is going to be 3 times 4 over n. So we have 2 times 3 times 4 over n, or 6 times 4 over n for the height there. And this just kind of keeps going. If I stop, you know, like, keeps going until we get like close to the end, right? Then we have our last two, x sub n minus 2. Well, that's going to be n minus 2. If this pattern continues, n minus 2 times 4 over n. And its height, I'm just going to double the x values. So 2 times n minus 2 times 4 over n. And our last one, x sub n minus 1, that's n minus 1 times 4 over n. And that, I'm just going to double that to get the height. Okay. So, so now we have this table made where we have the heights of all of these rectangles, right? Over on the right-hand column. We know that if we're going to find the approximate area using n rectangles, what we want to do is take delta x and multiply it by the sum of these heights. So our delta x is 4 over n, and the sum of these heights, that's just what we have here in the right column. So let me zoom out so I can get a good view of, see the whole thing. So now I'm just going to add them all together in here. So the right column, 0 plus 2 times 4 over n, plus 4 times 4 over n, plus 6 times 4 over n, and then we have tons of these, right? Lots of these. And then our last two look like 2n minus 2 times 4 over n, and then 2n minus 1 times 4 over n. Okay. Now we've encountered a substantial obstacle here in getting an expression of n. There were like a formula where we just plug n into to say, like, if I wanted to know what the approximate area is, if I'm using 100 rectangles, I just plug in n equals 100, and the obstacle is right here in the middle. It's all this dot dot dot. Like, I know what each term is going to look like, but I don't have like this closed formula that I get to use that just spits out a value. So what we're going to do is a little pattern recognition. First of all, we all understand that, you know, the 0 there doesn't matter, so I'm going to throw that term out. But also each term has a factor of 2, right? Also, each term has a factor of 4 over n. So I'm going to factor out the 4 over n. So I'm factoring out the 2 and the 4 over n. And then what's left? Well, if I factor out the 2 and the 4 over n, then this is just 1. This needs a factor of 2, that needs a factor of 3. So we're just adding the integers, 1, 2, 3, all the way up to here. This will need a factor of n minus 2, and then we'll need a factor of n minus 1, so plus n minus 2 plus n minus 1. The bit in the beginning here will simplify a little bit because I got 2 factors of 4 over n. So I've got 2 times 4 over n squared. And then what's inside? We're going to simplify this sum, right? We still have this dot dot dot, but we're at the point where we can actually get rid of it. And here's how we understand, here's how we could see what this sum is going to end up being. If I were to add the first and the last, 1 plus n minus 1, that adds up to n. And then if I move in 1 each, 2 plus n minus 2, that adds up to n. If I keep going, 3 plus n minus 3, that adds up to n. As I pick off these terms in pairs, like on the outsides, and kind of keep moving in, each pair adds up to n, and since it takes 2 of them to make an n, then I have n minus 1 over 2 n's that we're adding together, right? Like I've got n minus 1 integers here, right, from 1 to n minus 1. It takes 2 of them to add up to n. So I've got n that I'm adding to itself, n minus 1 over 2 times. And there's the sum of the first n minus 1 integers. Do a little bit of simplifying here. The 2's cancel. I'm running out of room on this page, but I've already added, I've accounted for that room that's needed. So moving down on the next page, I'm going to square out the 4 over n squared. So we have 16 over n squared times n minus 1 over 2. Yep. Oh no, not over 2. I've already canceled the 2. Sorry about that. I can cancel an n here. So now we have 16 times n minus 1 over n. So if I wanted to approximate with 100 rectangles, I just plug in n equals 100. I don't have to draw 100 rectangles. I don't have to add up 100 heights and multiply by the width. So we know how to get an approximation using n rectangles. Now, that wasn't the title of this subsection. This subsection talked about finding an exact area under a curve. So to get the exact area, we want to let the number of rectangles approach infinity. But we know how to do this. This is a limit, right? We're going to find the limit of a sub n as n approaches infinity. So the exact area is the limit as n approaches infinity of the approximate area with n rectangles. That's generally true. Now we're just going to apply it in this particular situation. This is the limit as n approaches infinity of 16 times n minus 1 over n. So 16 n minus 16 over n. Now, it's been a while since we've done limits as n approaches infinity. We did a little bit when we did some curve sketching. But our basic approach algebraically here is to multiply the top and the bottom by 1 over the highest power of n that appears. So I'm going to multiply top and bottom by 1 over n. And that is, when we distribute up top, 16 minus 16 over n. And on the bottom we just get 1. Now as n approaches infinity, 16 over n approaches 0, and this whole thing just ends up being 16. There's our exact area. Now, if we go back up and look at that region, like I said in the beginning, this is a sort of a simple geometric region. That's a right triangle. It's a right triangle whose base and height are 4 and 8, and if you use 1/2 base height, you'll get 16. So what we've done, hopefully that lends some validity, some legitimacy to the process. That feels like kind of a bit of a convoluted process. I have good news for you. When we're finding the exact area under a curve, we're not going to really need to go through this process. Like I said in the beginning of this whole section, that this section feels like a bit of a diversion from what we'd been doing the last couple sections with integration. But we're about to kind of connect those dots right now. As it turns out, we can find the exact area under a curve by integration. So if I want the area under a curve from x equals a to x equals b, which we're just going to denote in that fashion for now, we're going to integrate the function. But we're going to plug in some numbers after. So we have a bit of new notation here. I've got these values that we're kind of writing on the bottom and the top of this integral sign. These are called limits of integration. And what this means is you integrate the function and then you plug in the upper limit first. And then the lower limit, and then you do some subtraction. So calculating this involves finding an indefinite integral, like the same process of finding an antiderivative. But in this process, when we're integrating in this way in order to find an actual value, and we're going to plug in numbers, big F of x can just be an antiderivative. Any antiderivative will do. So we don't need the plus c when we do this integral to get a result. So here's that first function that we looked at, that we did, about 3 approximations using this function. Now we're going to find the exact area under this curve. So the exact area under this curve from 0 to 4 is the integral from 0 to 4 of the function x squared plus 1 with respect to x. We're going to integrate this function. X squared, using the power rule, we get 1/3 x cubed. Integrating 1, we get x. I don't need to worry about a plus c here because we're going to be plugging in values and doing some subtraction. Now, when I'm going to just sort of draw your attention to a bit of notation. When I integrated, I put it in brackets, and then I wrote these limits over again. And it's the upper limit on top, the lower limit on the bottom. I wrote these limits on the right side. That's pretty standard in math and engineering, that we write out when we're evaluating. We put those values on the right side of the brackets. Now what this means is, going up here with this result, is I'm going to plug in the upper limit first. So 1/3 times 4 cubed plus 4, there's the f of the upper limit, minus plugging in the lower limit, 1/3 times 0 cubed plus 0. Now as it turns out, when we plug in 0, we do in fact get 0. That doesn't always happen, but that zeroes out. So we're just going to evaluate this first one. 1/3 times 4 cubed plus 4 is 76/3, or approximately 25 1/3, or 0.33. So this is a little bit more than our last approximation. So if you go back to the example where we used 8 rectangles, we got an approximation of 21.5, about 21.5. So we were a little close with 8 rectangles. On exercises, there's going to be problems where they ask you to find an approximate area using left endpoints or right endpoints, left sums or right sums, they might refer to them as. There may be some where they ask you to find an exact area, and when they do, they mean using this technique here with the integral, not necessarily by trying to set up the limit like we did on the last one. But we have now a sort of a geometric or kind of physical sense of what integration can be. With the derivative, we know a derivative is like a slope of a tangent line. That's how we connect it to a graph of a function. With the integral, it's the area under a curve. It is a way that we can write, that we can kind of add up infinitely many things that are infinitely small, kind of like a magic adding machine. This process where we find this integral and plug in some values that we just went through in this example here is like a magic adding machine. This takes the place of adding infinitely many rectangles together.